Huh? Give me 1 second. This something's wrong with the projector. Huh? Sorry, guys. Okay, we can still do this. You guys have a screen. Okay, I can record.
Recording in progress.
Good. Uh, 1 second. I want to test my microphone. Okay. That's fine. 1 second.
Recording stopped.
Why is it not working? One sec. Sorry about the delay. Something's wrong. A lot of things are wrong with my computer and supporting systems.
Recording in progress.
Okay, let's continue from last time. We're learning bracket notation, right? So to give you a reminder, this is cat quantum state. Bra is a kind of an operator. Okay, it does something to the cat, right? And this cat is, you express it as a column matrix, and then bra is expressed as a row matrix, and then with the same like thing in the middle, if you change the cat from cat to bra, you actually make it a row matrix. It's a complex transpose, right? You make it transpose it at the same time you take the complex conjugate of the original numbers. That's the rule. And then we just like learn how this rule works for a while, okay? This is the quantum mechanics formalism, so we're learning about the rule. It's like we learn about the rule of the sports game. So there's nothing really difficult. It's a rule. And then this rule works beautifully for all the formalism of quantum mechanics, and it's very convenient. So let's see how it works. Okay, so also the bracket notation also allows that kind of sandwiching the operator in the middle between bra and cat. And then actually this is defined as, also you can think of it as just the bracket, the inner product, and also the inner product of these two. And then I haven't written important information here that the K, right, the K cat, the quantum state is given as this one. Okay, operator, or the interpret it, right? So when you do this, right, you first apply this operator, okay, the one in the middle operator, to the quantum state, and then you get another quantum state, psi k. With that psi k and the original bra, psi I, you take the inner product, okay? You interpret that way, or the new one, I introduced the one, right? This bra of psi L, that is defined as, oh, well, actually, let me write it this way. Psi L is something like, uh, okay. This one, you can write it this way. And then if you look at for the first time, it's not really like, you may not feel this is like what it means, right? So actually, if you take the complex conjugate, complex transpose, right, you turn the bra into cat, and then it's a bit easier to interpret. And then when you in matrix, right, it's the same with the matrix. When you take the complex transpose, right, then you change the order of matrix, right, and then take each of them complex transpose, right? That's what I'm doing. Okay, it's this one. All right. So that psi L is the one there where you apply O dagger, which means complex transpose, right? Apply to psi I as a cat, okay? And then you get quantum state, which is psi L. And then you turn this into a bra shape, right? And then the original psi j, you take the inner product, okay? That's the rule of the bracket notation. So to wrap up, right, there are lots of ways of rewriting this. You can also choose to write this way, okay? It's a bit clearer, right, what it means. You apply that operator to quantum state and then get and then so if you look at the picture of applying operator to the bra left hand side, you can write it this way, okay? So this way you kind of get a clear feel for what it means, all right? So let's apply this to a particular example of how you calculate energy expectation value, the operator corresponding to the Hamiltonian operator. So to a quantum state psi I, you apply Hamiltonian, and then we have already been doing this, which is you get E psi I, right? You just get a quantum state, E is multiplied to it, right? If you apply Hamiltonian to an energy eigenstate, and then actually, I write EI, and then you get EI psi I. The number can get out of this inner product, and it's normalized, you get EI, okay? It's just one example of how you apply this. And then if you have a bit more complex situation where you have two separate operators that sandwich in the middle, but that's still right, not very difficult. If you think about what it really means, what it really means is that you can actually do something like this, okay? So you move the O to the left, right? R to the right. You can do this way, right? You apply O to the left and apply O dagger to psi I, you'll get a quantum state, and then you take the brush shape of it and then take inner product that R with RJ. Or this is also equivalent to way of writing it. You can still leave R as in the middle, right? That's also fine. Also, from here, right, you can actually think that, okay, you can actually move R to the left as well. So what you have here is that this one. So this one was there, right? So to this quantum state, I'm applying R dagger and then make it bra, right? So you can do this as well. And then, well, you can choose to just write everything without that parenthesis, right? So R and O all move to the left. And then when you go there, right, you can see that OR, the order is swapped, right? Because you take the transpose, complex transpose, or you need to swap its orders. And then you can move all the R and O to the left as well. In that case, you can choose to write it as O R applied to psi j, okay? So they all mean the same thing, but it kind of expresses how you actually calculate or how you think the physics. All right. So they're all equivalent. And then remember, if you have this operator combined together, if you take the complex transpose, you take each of it and then swap its order. All right. Same with the matrix. Okay. Second. So that was a bracket, and then next one. So I mentioned the bracket, you can the cat you can make a link to the column vector, right? Bra as a row vector. So I'll look a little bit more into it and explain what it really means, okay? So we will learn for a while the matrix formalism. So it's a lot like linear algebra if you already have learned, okay? It's all about like dealing with the matrix. So to make it simple, I will start with an easy example. All right, easy example of something like a spin. Okay, we'll learn spin later. But like if you have an electron spin, right? Electron spin is very, very simple object. So it's relatively easy to understand, but it's a quantum object. All right. So assume there are two eigenstates, okay? Single electron, actually, it does have two eigenstates in terms of its spin. And they are complete. So electron spin is a good example. Okay, so you can think of it as a magnet, okay, bar magnet, something like this. And then if you put your spin, right? So there needs to be a reference, but it's along some axis, right? And then you can encode it as a quantum state up, spin up state. And then if it's pointing down, you flip it, you can mark this way, okay? So it's same with the quantum computer's qubit. So quantum computer's qubit can be made out of many different things, but electron spin is a good one example. Okay, it's a very good example how you can build a qubit out of electron spin. All right, so that's a spin, and then like for single electron, it works, okay, quantum mechanics works, and then that way of encoding, right, actually it used to be a mainstream like storage solution when I was young and around 1990s, before most of you guys were born. Like there was this thing called a hard drive. Hard drive. You store your like data in computer, and then that time it was a magnetic material, and then like whether this n is pointing this way and this way was representing 0 and 1, but that's a classical. Okay, that's like this is just a digital computer. And then it's non-volatile, right? So these days there are like many different ways, but anyways, it's one way of encoding information. North pole, south pole, n is where pointing where is a good way of representing 0 and 1, and it's a quantum object, so it can have a superposition, all these things, quantum mechanics phenomena you can have. Okay, so let's continue. So this quantum state, right? Let me use just the 1 and 2, okay? I'll use the 1 and 2 represent these things. 1 and 2, 0 and whatever. So it's you can just like use whatever you want. Let me see with the 1 and 2. I think it may give you confusion. I'll just work with the 0 and 1, okay? Qubit 0 and 1. Okay, I'll work the 0 and 1, okay, to make things simple. And then since it's a quantum state, your electron spin, in fact, can be expressed as something like spin up state and spin down state superposition is possible, okay? And this one you can write as a matrix by saying that, okay, so this spin up state is an eigenstate, okay? So we'll make this as your basis, all right? So do you remember that like our particle in the box problem, there are infinite numbers of energy eigenstate and they're complete. What it means is that any quantum state for this system can be expressed as a linear superposition of these energy eigenstates. So that means it's a complete. In spin, it's actually these two are already complete. Any spin state of electron can be just expressed that way. All right, that's why in that sense I called it simple. So one is we agree to write as this, okay? So whenever we work with the matrix, there is a always assumed eigenstates, okay? There is an assumed eigenstate for the matrix notation. All right, so there is some complex thing is hidden. For example, here we don't really write, that spin-up state is like, sine kx divided by L, these kind of a complex expression we used in particle in the box, right? So all these like complex math equations are all hidden, okay? They're not shown explicitly in this notation. So it is quite nice because you just like forget about all these complications and work with a nice simple matrix. It's possible to do so if it's possible to limit ourselves to linear algebra because quantum mechanics is linear. It is linear and it allows superposition, right? Because it's linear, it allows superposition. So we can build all of our solutions with a linear sum. That allows us to work with the matrix. So, sorry, I think, okay, I'll work with a 0 and 1. 0 and 1. Okay. And then, so you can easily see, right, what matrix I'm going to write. It's going to be C1 and C2, right? It's a usual matrix rule. Okay, that's how you use a matrix to represent the quantum state. So quantum state is a vector. Let me use a red one, vector. And can be written as a column matrix. Right. So this is not just true for quantum mechanics. It's also used in like usual linear algebra as well, right? If you have learned something like this, right? If you have a vector, right? So the basic geometrical vector, you write it this way, and then this one is x and y coordinate, right? And then in linear algebra, you learn that actually you can write it this way, right? And then you call column matrix as a vector, right? So that's what you learn from linear algebra. So we'll use the same concept in quantum mechanics. Okay, so it's from linear algebra. And then in that case, right, your x direction unit vector, you, 1 second, express it as 1, 0, right? Y as 1, 0, okay, 0, 1. And then their linear sum, right, is what? AB. Okay, the same concept goes here, but it kind of generalized in quantum mechanics because geometrical vector, you always work with like 2D, 3D, right? But like you can do infinite dimension in quantum mechanics or any dimension. And we will learn the operator as a matrix. This is a fun part. Linear transformation. Okay, these operators changing quantum state from one to the other in quantum mechanics is all linear transformation. All right, it's all linear transformation. So when you do linear transformation, actually what it means is that you have these like bases, right? Bases, like basically your basic ingredients. For example, in geometrical vector x, y, z are unit vectors, right? So basically all about you put some weight there and then add them up, all right? That's what you do. So linear transformation, just multiply some number, in this case, quantum mechanics, you're allowed to multiply complex numbers. You can have phase information. You can multiply with the complex numbers and add them up. That's linear transformation. So I'll give you an example of how that's working. So let's say I apply some operator q to psi, and then let's say it becomes phi. Okay, then phi is, let's say it's this expression. Okay, so in matrix language, I can express it as this, right? Mm. Okay, I remembered why I chose 1 and 2. Okay, sorry about that. I'm going to fix it. I think 1 and 2 is gives me a nicer notation later on. So let me switch to 1 and 2. It's you will see the reason why later. 1 and 2. Okay, I'll go with 1 and 2. So anyways, Q is applied to psi, and then you can represent Q as this square matrix. One second. There was an error with my iPad. Okay, I'll do it again. Let's do again. Okay, let's continue. Okay, Q12, Q21, Q22, the usual matrix. And you apply it to C1 and C2, and then you get D1 and D2. That's all about it. Okay, your Q is just that, okay? That operator is a matrix. Okay, then we wrote that Q1 and Q2, right? Let's say, okay, the Q11, Q12, these numbers are what, right? These numbers are what? So there is a very nice way of expressing it. Let's say I have 1, 0. I want to extract Q11 in this case, Q11. And then all other three, I'll just discard, right? Then you can easily justify, if you, if you do it, you just get Q11. And then you can keep doing the exact same thing. Okay, let me go a bit quicker. 1, 0, 1, 0, the same matrix. This time 0, 1, all right? 0, 1, and then you get Q12, 0, 1, Q11, Q21, Q12, Q22, 1, 0, Q21. Lastly, 0, 1, the same thing. Well, this looks trivial, but I've done it intentionally just to show that it really links nicely with the bracket notation if you do so. So let me show you why. So this part, right, it's a unit vector, right, of 1, 0, written in what form? That row form, right? So remember, that was a bra. So it's what? It's 1, okay? This matrix is Q operator, right? It's linked with that. And then this is what? It's 1 cat, right? And then you can do the same thing for all the other matrix row and column. So if you summarize, you can actually write it as one simple form, which is Qij, the number of the matrix, okay? The element of the matrix is written as IQJ, okay? So bracket notation, Q sandwich in the middle, right? That's how you can extract that number from the operator. And then K is a column matrix where only kth component is 1 and others are zeros, right? Okay, so this is a notation. So this linear algebra, right? It gives you a lot of nice features, and then I'll write one of them. So this linear transformation, right? Linear transformation. So let's say you don't know what Q is yet. Let's say, okay, you want to figure out this operator is what, right? Then what you need to do is, right, you apply this operator. You don't need to test a lot of inputs. You just need to test all the bases and then figure out this basis becomes what. Then you know this matrix fully. So I can mathematically prove it right here. Okay, so let me write it for all eigenstates. For all eigenstates in a complete set, okay? Complete set. So gives a linear conversion formula. Okay, and then you put together, it becomes the entire matrix. So let's say you have this input of 1, 0, and then you apply this operator to this quantum state, and then what happens? That's essentially you're calculating this, right? If you calculate that, you can extract the left column of the matrix. You get Q11, Q21, right? And then if you have this, which is 1, 0, you apply Q operator there. What you're essentially doing is you're doing this calculation, and then it's going to extract the second column of that matrix, right? So it gives you Q12, Q22. Okay. So once we figure out, right, we actually were ready to calculate Q is transforming any arbitrary input to what? Okay, we are ready to calculate because of this linear combination property for any psi, okay, for any psi, which can be written as C11 plus a C22, okay, some random number comes in. So if you apply Q, okay, what's going to happen is already we know, right? Because separately it does what, right? So for the blue term, right, we know what's going to happen. It will become this expression, right? We already know the answer for the basis factor, and then we just multiply the coefficient. So we know that for that term, it is that answer. Okay, it has that response. But it's a superposition, right? At the same time, the red one is working, right? Red one is being transformed into this expression, C2Q12, Q22, right? And then you can add up. Okay, that's going to be D1, D2. That's how you think this matrix formula is, the operator, okay? So if you have this big matrix of an operator, like you slice each column, and then each column is actually expressing how you transform each basis. Okay, you collect those numbers and write column. You collect those numbers, write a second column. That's how you make your matrix. Of course, this example is small matrix because we're working with the spin, but it can be extended to arbitrary number of dimension. Okay, so let's test it to our famous example of Hamiltonian operator. If you apply this, okay, it's an energy eigenstate, so it makes an energy eigenstate answer. You apply to another energy eigenstate basis, let's say. Okay, so this 1, 0 is you can call it energy eigenstate, okay? In fact, spin state is also energy eigenstate. So 0, 0, 1. Then H is what? You know, H matrix is in this form, right? Diagonal matrix. And it's not a coincidence because I've mentioned, right, whenever we write matrix, there is an underlying assumption that we're using this kind of basis, okay? So what I've just used is actually an energy eigenstate as a basis, right? With that basis, if it's energy eigenstate basis, and I wanted to express my energy operator, right? Hamiltonian, basically. Energy operator, I express energy operator with the energy eigenbasis, you end up getting diagonal matrix with the numbers are all energy eigenvalues listed. Diagonal matrix, since we are using energy eigenstate basis. So which means that if you have even for the same system, right, there can be another basis, complete basis, right? So if you use another basis and try to express Hamiltonian, right, it may not be diagonal matrix. It can be some complex different form of matrix. It's possible, okay? But let's say if you have a basis of some sort of let's say momentum eigenstates as a basis, and then you express your momentum operator as a matrix, and you will get the same behavior. Diagonal matrix is all the momentum eigenvalues listed diagonally, okay? So let's move on to the next example of matrix applied to inner product. So inner product in a unified picture, okay? So far, we have learned inner product in two different ways. The original was this spatial integral. The second, I taught you how to do it with the bracket notation, but at the same time, bracket notation becomes matrix, right? So these three pictures, we'll see how they can be nicely combined, and basically like they're not contradicting each other. They're working nicely together, right? And then you have these like a lot of different tools to calculate or see things, right? I mean, from different angles. So let's say we're handling something like particle in the box problem where you have an infinite number of energy eigenstates. And then according to our discussion, so let's say use this basis, and then your matrix is something like C1, C2, so on, right? Yeah. So what I wrote in as a sigma, if I write it as a column matrix, it'll become that form. So I use these three dots to express that it can be even applied to infinite number of eigenstates. And then your cat of this is simple, right? You take the transpose and complex numbers, complex conjugate. 1 second, let me add one more number here. Okay, that's a bra. And then let's see, for example, like the Born rule, when we did the Born rule calculation, it's kind of inner product with itself, right? That expression. So that one, let's see how it works. As a simple example, you can write it as this, right? Self inner product in spatial integral form. And then what I'm going to do is that I'll replace this with the sigma expression I used up there. Right, this is what you calculate. So if you do so, what happens? If you write down, I'll take out all the sigma signs outside, right? Sigma signs outside. 1 second. This one, I need to use M. N and M. And then these numbers are here, and then it needs to be NX, MX, DX, right? This is the algebra. It's a mathematics rule. And then next important thing is what? They are all chronicle deltas, right? Because I'm assuming they're normalized already. So you get this. Sorry, CNM is CN, CM, chronicle delta NM is there. So what you get? You get NMN need to be equal to be non-zero, right? If they're different, it's zero, right? Because they're orthogonal. So what do you get? You get Cn epsilon square, right? You add up all the coefficients, all right? And then, so let's link it with matrix, okay, matrix notation. So this one, right, is in fact the same as this, right? Inner product of itself, right? The expression is this. And then its matrix form is what? C1, C2, C3, so on, and C1, C2, C3, so on, right? And then you can see this one and this expression is as we have learned, right? As it's according to our definition. And this one is also as according to our definition. And you can see this end result is same with this, right? You get calculation, you will get that. So these formulas work nicely with each other. All right. So matrix, bracket notation, and then spatial integral. It doesn't have to be spatial integral, but it's continuous variable integral, basically. Okay, they can work together like this. Okay, so it's a trivial thing, but let's for completeness, let me just do it. So let me make a real inner product between two different quantum states. Okay, let's say I have something like this. Now it's phi, and then so the coefficients are all different. In this case, you can think of psi and phi and psi, their inner product, right? And then how do? You have this row matrix, and there will be column matrix C1, C2, C3, so on. And then that is supposed to be the same as this, right? Our spatial integral definition of inner product. They're all equivalent. What else? Okay. Let's see. See, it's kind of usually in science, okay, in science and engineering, actually, have you guys heard of this thing called a sanity check? Sanity check is nothing but, checking if we're doing anything crazy, okay? So sanity check means that something trivial, you think it has to work, you just give it a try and see if everything is consistent and there's no error. So I'll do sanity check here. So my sanity check here is that so that inner product is giving you what? It's a number, okay? It's a complex number as a result of inner product, right? So in that complex number, I can take a complex conjugate. And this complex conjugate applied to bracket, we have learned all the rules today, right? Bracket, you have apply, you swap its orders and do this, do that. And then you guys all know how you apply this complex conjugate to integral as well, right? You guys have learned how to do integral. So all of these things are working fine. We'll check. So let's do this. So basically the row above, I have this, right? One second. I think a notation needs to be consistent. There is this phi is a bit different from what I just have used. So that was the expression, and then I'm taking the entire thing complex conjugate. Okay, so for the complex number, I take the complex conjugate and see all the rules are working fine. And then, so this moment we just focus on the integral form, and then this one is nothing but, integrand, I apply that star, right? And then add up. So, and then since they're just numbers, there's no problem changing their orders, right? So I can do this. And then this one, right? If I write this one, compare this with this one, right? Then what is that? If you have this, okay, this one becomes row vector, this one becomes a column vector, okay, but this time phi and psi are flipped. So it's going to be C1 star, C2 star, C3 star, so on, D1, D2, D3, so on, right? And then this one, right? So go back to how that was working, right? The way you convert this bracket inner product to that row column rule, if you do it in a reverse direction, then you get the obviously correct result that the one you expected and the one I showed you previously today. All right, everything's working fine. Sanity checked, passed, good. So let me wrap up with introducing some definition of the length of a vector is a self inner product, okay? Inner product, and then you'll get some number, and then you take square root of it. That's the length of a vector. Vector means the quantum state or cat. Okay, so the quantum state, you can define this length, okay? This length, of course, it works in a usual length as in geometrical vector, right? Geometrical vector has this arrow and you can measure its length, right? But I told you that vector also you can write it as a column matrix and then you apply this rule. This rule is actually corresponding to that vector. However, in quantum mechanics, it's more abstract. It works in a more abstract world, right? It doesn't really have to be that like geometrical arrow. However, you still define the length as this, the same way. So in linear algebra also, you define the vector length as this. So it's the same definition, okay? Linear algebra and geometrical vector. Vector is physical length. So it's working nicely. And then to wrap up, right, I'm just writing up. So we start from calculus approach, right? We had this integral, which is familiar to most of you guys in the beginning. It's more, direct first time. If you at the first sight, it's more like direct expression of what you're familiar with. And then we introduced this a little bit exotic new way of writing things, but it makes it simple, right? Bracket. Then lastly, matrix as a tool for linear algebra. What we showed was their relationship, okay, between these three. So today, everything is not honestly like, it's a bit new to you, so not familiar maybe, but actually it's not difficult at all because it's learning about the rule. Okay, this is just the rule. There's not like serious concept or like you need to think hard. It's more about a rule, and then this new rule of formalism is useful. Okay, useful tool for calculating things. Think about quantum mechanics. That's why we learn all these three aspects. All right, so let's move on, and then so now let's explore matrix more by working through like different examples. So let's start with the Easystone identity matrix. So identity matrix is what? It's just like you apply this to a quantum state. As the name suggests, it doesn't do anything. It itself, right, gives itself. Okay, identity matrix. Of course, you learn it from just the linear algebra. But in quantum mechanics, there are some fun things to do with even with the identity matrix. You'll see. So let's say if complete set is given. Okay, let's say there's a complete set and some arbitrary quantum state is a linear superposition of this basis. And then, okay, so from here we can play a lot of fun tricks. You remember, actually, we have learned this like in the very beginning. If you have a superposition of this like many bases, and then you want to extract one coefficient, right? We learned how to do. How do you do? You take the inner product with some basis, right? And then it only extracts that coefficient because all the others are zero because orthogonal. So let's do that. To this quantum state, if I apply J eigenstate to a given quantum state, the arbitrary superposition of it, now actually this like expression is now becoming quite simple because if you remember, the way we used to do this calculation was a space integral, and then you have to write down all this complex integral. But the bracket gives you a very nice simple notation. Now you are doing this, right? Yeah, it is this way. Okay. Then you only filter out CJ, right? So from that, right? So I'll apply this to a one above, the row above, the black one, the one I'm writing. So instead of writing CI, I'm going to write it as this. I will filter out and get CI as this, okay? See, this is CI. This bracket is CI, right? So that will give you CI, right? And then psi I was here. It's a kind of a weird notation, but it's nothing. If you have a bracket, it will give you a number. It's just a number, okay? So now bracket and cat is there, but no problem, just a number. Number applied to cat is what we're doing. And then, okay, what I'm going to do is that, going to now is, okay, you just said it's just a number, okay? So the number and the column matrix, right? Well, you can swap its orders. There's no confusion, right? So I'll send it to on the right-hand side, okay? Okay, now it's becoming quite interesting. It's cat bra cat. Okay, cat bra cat. But there's no problem doing so. It is correct. You can convince yourself by doing all the calculation yourself. And then they are all matrices, right? So matrices. So all the matrix rules you have learned are all applying here. So let's do that together. So let me write down again here at the bottom. There was a sigma, and then cat bra, bra, and cat. Okay. So now, okay, we will use this rule called associative rule used in matrix. Associative rule was when you have an ABC matrix, you can multiply AB first and C is the same as A multiplied to BC. That was associative rule. So they are the same, right? They were the same. So what I'm going to say is that, okay, this form, when you think, right, when we think it's corresponding here, okay, BC first, okay, we do this first and then get CI and then multiply to this matrix, column matrix, okay? That's how we were thinking. But however, we can think this way as well, because they're the same, giving you the same result. So what I'm going to do is, uh, 1 second. Okay, let me move it. There's no space here. I'll do this. This one is one body, I'll think. Okay, I want to think as one body. And this one is a, remember, it's a cat, so its dimension is n by 1. Or let's say we're working to n dimension, okay? I forgot to mention here. So it's not infinite. Let's say it's n dimensional, okay? There's n number of bases. So it's n, and then bra is a row matrix, so it looks like one row, n elements, right? 1x(n), right? So if you multiply that, what do you get? N by n matrix, right? N by n matrix. So that the thing in the parenthesis is a matrix, square matrix actually. All right. The square matrix. And then let me call that square matrix as Q. But there is an index, right? I. So index I, I'll keep that index I. Qi is a square matrix, which is an operator. And then 1 second, that Qi is defined as this, okay? Cat bra. Cat bra is giving you the same quantum state cat and bra. If you do it, you'll get n by n matrix. And then obviously this one is the same with our original starting point psi, right? So instead of writing psi, let me write down some operator, identity operator, 1 and psi. Then what do you get? Our conclusion is the identity matrix is actually the same as this. Right? So with the eigenbasis, you can actually express your identity matrix with that nice form, cat bra form, summation of cat bra. All right. This is an eigenvector, the quantum state. And then there is a way of interpreting bra, which is something like here, what we have done here. So that bra psi j's role is what? You have a lot of terms, but actually you filter out just your target, right? So it's kind of a projector, okay, extract a target eigen, right, with the coefficient. So it kind of if you think about this, right, it's kind of it's correct and it looks nice, but it's actually its meaning is kind of trivial and it has to work because you apply that bra to a quantum state and then extract the coefficient of your target eigenstate. And then that number you apply to your eigenstate, okay, you have this result and you do it for all the eigenstates. And of course, you will produce yourself. Okay, so think about the meaning of that expression. So how the procedure works. You have a lot of summation of superposition and then you extract one of them and then, okay, this quantum state coefficient is what I take it out. That's the part you are doing with this part. And then you apply the number to here and then you do it for all the eigenstates. And then you repeat yourself. That's identity matrix. Okay. Okay, so it would be nice to write down the real matrix and then you'll get a better feel for how it's working. Basis, representation. So I'm using this basis for my matrices, all right? Then it's a bit tedious, but let me write. The first eigenstate is what? I'm just extending our, what is that, spin example, okay, to many dimension, big dimension. 1, 0, 0. Only the first one is 1. All the others are 0, right? That's how it works. Only the second eigenstate, you can assign 1 to second number only. You can keep doing it to, let me continue until 3. 0, 0, 1, 0, ongoing. And then let's specifically calculate this expression we just studied, right? What it becomes is 1, 0, 0, 1, 0, 0, right? It's a column and row, right? It's different from, it's the opposite of what we have learned. It's the inner product is was the opposite, right? And then you get one number. This is the opposite, right? Then you get n by n square matrix. This one, 1, 0, 0, 0, 0. Everything else is all 0, right? You get this matrix and you can imagine doing it for k eigenstate and calculate ket bra, all right? What is that? This will become 0, 0, 0, 0, 0, and then 1. And then this 1 is located at kth row, kth column. And 0 elsewhere. This is a matrix of that ket bra, okay? And then, okay, finally, let's move back to our original target of identity matrix, right? You add up all the matrix. Obviously, what is going to become is what? 1, 1, 1, ongoing. All the others are 0, right? And then that is the same as identity matrix. So everything's working fine with this formalism. And then bracket notation and everything, it fitting quite well. Okay, and the next one is very trivial. It's a inverse operator. Right? Since you guys have learned matrix, so inverse is easy to think, right? Operator is a matrix, so if the matrix is an inverse matrix, you can think of that operator as an inverse operator, right? So this inverse operator, the same as the matrix case, you can swap their orders, you get identity matrix. So finding inverse operator is becoming the same problem as finding inverse matrix, and which is well known, right? Which is known for matrix algebra. So for large dimension, of course, it's a lot of calculation, but small dimension, we all know that you can do this way, right? And then in general, for a matrix, the inverse is this. Okay, it's just we can use all the well-known facts from linear algebra. For inverse operator, okay, so next one is, okay, I think this one is the most important one. So unitary matrix. So unitary matrix is the most important one for quantum mechanics. Unitary matrix is actually, in linear algebra language, it has just this exotic feature of the condition. Okay, it needs to satisfy that. Your dagger, which is complex conjugate or Hermitian conjugate, Hermitian transpose, if you do that, actually you will get your inverse operator, inverse matrix. So it's not trivial. You have to satisfy the condition. So it's kind of a special matrix, right, that has that property. So let's say we have two dimension, okay, because it's simple. Let's work with this. Complex Hermitian transpose is what? You transpose, okay, you can see I changed the index, right? 1, 2 to 2, 1, 2, 1 to 1, 2. And take the complex conjugate for each element, right? That's the Hermitian transpose. And then somehow that is the same with the inverse matrix. Okay, that's a special condition. So because it's the inverse matrix, what it means is that Hermitian transpose and you multiply yourself, it will become identity matrix, right? That's a okay, that's a unitary matrix. And then let me see. So unitary matrix, right? Do we have time? Yeah, unitary matrix has two usage, okay? Two different concepts. So they are both important. This one. This one. Okay, first one is this example. This example is you see a lot from high school math problem. So it's a change of basis, okay? You have this, 1 second. You have this x point. X vector, okay, x vector here in the middle, x vector, right? X vector, it can read as x1 comma x2, or with another basis, right? Another basis, you can also read it as x1 prime comma x2 prime, right? Basis concept. The change of basis, you have learned how to express it in matrix, right? When you rotate something. So let me write that. x1, x2 prime, your output is related to your original coordinate, x1, x2, with the cosine sign minus sine cosine relationship, okay? So that's what I'm talking about, what you have learned in like high school mathematics, okay? So another thing, the rotation, right? Rotation there's another example of rotation conceptually is this one. They're different, okay? It's, one second, this one. So it's the same. It looks like seemingly the same. But here I want to talk about the concept of the vector v2, v1, both of these vectors, right? So actually I can write one of them as well. They are just you rotated vector itself, okay? So they look very, very similar, but like I'm conceptually like differentiating it. First one is like you have the thing is not changing, but you turn your head and reading different number. Second is that the thing itself I'm rotating. I'm changing that object, okay? So change of basis and rotation of vectors. Two different concepts are both unitary transformation, okay? So time is up. Let's continue next week. I will post homework. Okay, today I'll promise I already made it. I post the homework in the afternoon. There will be about 10 days given, all right?
Recording stopped.